This is magnetic braking with Faraday, Lab 5. So the purpose of the lab is to collect observational data of a bar magnet falling through a conductive tube of aluminum foil, computationally model the interaction between the magnet tube, and compare those computational predictions with the observed data. So the experimental time is 1.25 seconds, and the computational time is 1.45 seconds. So some fundamental principles is Biot-Savart law, the time derivative of magnetic flux, Faraday's law, and Ohm's law. So the magnet is actually modeled as a magnetic dipole, and the aluminum foil is modeled as a tube through which the bar magnet falls through. And some assumption is that the air resistance on the bar magnet is negligible, and the only forces acting on the tube is gravity and magnetic force. So the system is actually going to be the bar magnet and the aluminum tube, and the surroundings, everything else around it. So for procedure, we're going to mark the north pole of the magnet using a magnometer, which is on my phone, and we're going to record the time it takes for the bar magnet to fall through the tube 5 times, and we're going to take the average of those 5 times to determine the average time taken for the bar magnet to fall through the tube. So here's all the results right over here, and for the average time, it's going to be 1.25 seconds. And right over here to the right, we have the length, width, radius, inner radius, mass of magnet, and mu from lab 3. And all of this is going to be used into our computational model. So right here in our glossary code, we have the physical constants. Right here, we put all that information, the geometry, the length, width, inner radius, the whole radius. We have mass and mu. And right over here, we're actually calculating the Biot-Savart equation, as seen by calculating R mag, R hat. And right over here, we're calculating d flux over dt, and this equation was seen as before in the fundamental principles, and the distance is calculated by the position of the ring minus position of the bar. And right over here, we have F gravity, which is going to be negative mg, mass times g, which is the gravitational constant. And right over here, the ring current is going to be negative d flux dt over the radius of the ring. And then right over here, we're calculating the B field at each ring. So we're going to do B hat, which is B at ring, and then the magnitude of that. And we're going to plug that into the equation. And right here, the F magnetic field is actually going to be in the y-axis, since it's only moving in the y-axis. And F net is going to be the total forces acting in the system, which once again is going to be the force of gravity and force of magnetic. And right over here, we calculate velocity and the position of the bar magnet using Newton's second law. So when that's seen right over here, where we have the blue ring and the red ring, this is our graph, and these rings move down in the span of 1.45 seconds. So potential sources of error is that there's human error during calculations, there's existence of air resistance, there might be error in the magnetic dipole found in lab 3, and there's different resistivity of the aluminum. So the red ring is actually shows counterclockwise movement, and blue is clockwise. So this was determined using Lenz's law and analyzing the direction of the magnetic field from the magnet. If we were to flip the magnet, the red and blue rings would swap, so the currents would flip directions. And however, the system would still behave the same and look the same on the visual level. The model time is actually slightly faster than the experimental time. The model could be more accurate by incorporating air resistance or determining the exact resistance of the aluminum foil and finding a dipole moment of the magnet with a better method. And the force of gravity and magnetic force are actually equal and opposite to one another, and that kind of allows the magnet to travel at a constant velocity as it falls through the tube. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the flowing magnet change? So the current induced in the tube would be much greater according to Ohm's law. Therefore, the magnetic force would be much greater, causing the magnet to fall slowly or even be suspended to the tube. So what if holes or slots were cut into a tube? How would this affect the ring currents in your model? There would be less current rings within the tube. Therefore, less currents mean there'll be less opposing forces within that tube, and it'll lead the magnet to fall faster too. So the period of time it takes for the magnet to fall through the tube would actually decrease compared to our original model. Okay, thank you.